Hello, and welcome to the sixth in a series of films about the standard level organic topic. In the first 5 films, we've looked at what we mean by a homologous series, and we've looked at 2 different homologous series, the alkanes and the alkenes. Here we're going to be focusing on the alkanes once again, and in particular on their chemical reactions. So hopefully by the end of this film, you will understand first of all what it is about alkanes that means they don't particularly like reacting with other things. And then for the things that they do like reacting with, you're going to be able to write some equations. So you'll be able to write equations for complete and incomplete combustion reactions, and also for the reactions of alkanes with halogens. And what is more, for the reactions with halogens, you'll know what we mean by a free radical mechanism. Okay, so if we start off by looking at why it is that alkanes don't really like reacting with other things. You might remember that we termed alkanes saturated when we were introducing this homologous series, and that means that they're already full, if you like, that we have to break some bonds and remove some atoms before we can put new atoms into the molecule. So one way of explaining why they're so unreactive would be to look at the bond enthalpies in the molecules, right? Because if you've got a high bond enthalpy, that means you're a bond that is difficult to break. And the bonds between single bonds between carbons and hydrogens and carbons tend to have quite high bond enthalpies, so they're hard to break. So before we can add anything here, we've got to break quite strong bonds, and that's a difficult thing to do. We could also look at this in terms of bond polarity, and this is a little bit more complicated, but we don't have to understand it fully. Okay? Bond polarity arises as a result of an electronegativity difference between atoms. And this can lead to a kind of imbalance of electron density around the molecule. And quite often reactions will happen because things will attack regions of high or low electron density. However, if you've got atoms that have quite similar electronegativities, then the bonds won't be very polar. So because carbon and hydrogen are quite similar in their electronegativity, carbon-hydrogen bonds aren't very polar. The electrons are quite evenly spread throughout the molecule, and so these molecules don't react very much. Okay, so you don't have to explain that in a great deal of detail, but you do need to be able to say that because the bond enthalpies are high and because the bond polarity is low, alkanes tend to be unreactive molecules. Now then, let's have a look at some of the reactions that they do take part in. Now, all hydrocarbons, not just alkanes, but all hydrocarbons can burn quite well, which is why we use them as fuels. So combustion is a reaction with oxygen, combustion just being another name for burning. So if we think about how we're going to write equations for this, well, we can think of any particular alkane, like methane, for example, and if we're going to write an equation for it, then we're going to need to include oxygen as one of our reactants, because combustion is a reaction with oxygen. Now, we're talking here about complete combustion. Complete combustion means that the carbons get as much oxygen as they can, and so do the hydrogens when we come to deciding the products. So potentially, if carbon were to combine with oxygen, you could imagine it forming carbon monoxide or carbon dioxide. But if we were to give it its maximum amount of oxygen, it forms carbon dioxide. There is only one oxide of hydrogen, and that's water. So in any complete combustion reaction, these are going to be our products, carbon dioxide and water. Writing the equation now is just all that's left really is to balance it. Now the number of carbon dioxides will always be the same as the number of carbons in your hydrocarbon, and the number of waters will always be the same as half the number of hydrogens in your hydrocarbon. So there'll be 2 water molecules here, right? 1 carbon dioxide. Now all that's left is to do the oxygens, and we've got 2 oxygen atoms here, another 2 there, so we need 4 on the left, so we're going to need 2 O2s. Now you could say this is a little bit easier when the number of carbon atoms in the hydrocarbon or in the alkane is an odd number, and we'll see why in just a moment, because I'll just do one quickly for ethane where we've got an even number of carbon atoms. And once again, combustion involves oxygen, and if it's complete combustion, then we're going to be making carbon dioxide and water. And then this time we're going to make 2 carbon dioxides and we're going to make 3 waters. Now what you'll see with any alkane that contains an even number of carbons, you'll end up with an odd number of oxygens on this side. Okay, so we've got 4 oxygen atoms here and 3 there, so 7 in total. So we need 3.5 O2s. Now that equation can be left just like that, if you like, but some people get a little bit upset by the presence of these half numbers. So if we wanted to, we could double everything in this equation. We could make that 2 ethanes, 7 oxygens makes 4 carbon dioxides and 6 waters. Either one of those equations being just as good as the other. The key point about complete combustion equations is not only that they balance, but they contain carbon dioxide and water as their products. Now, if we contrast that with incomplete combustion, this is when there's a lack of oxygen. So often gas heaters, for example, get tested to see if they're working properly, which means is there a sufficient supply of oxygen to the fuel, because if there isn't, then the carbon in the alkane could just be left as carbon, or more importantly, or more dangerously, it could turn into carbon monoxide instead of carbon dioxide. And the danger with that is it's a very poisonous gas, but it doesn't smell of anything. So if you're producing it in your home, it's not really a very good thing. Okay, so if we think about writing balanced equations now, what we need to make sure we do is that we include at least one of those things, or any combination of them. Okay, because how much carbon and carbon monoxide you produce depends on how much oxygen you have. And if someone tells you that you're incompletely combusting a fuel, they're not often going to tell you about the amount of oxygen you've got. So you're kind of free to write a number of different equations here. So for example, I could write carbon as my only carbon containing product and 2 H2Os, because I've still got 4 hydrogens, and we have to make water because it's the only oxide of hydrogen. And that equation is balanced. And you could imagine this reaction happening in a Bunsen burner where the air hole was closed, because there wouldn't be very much oxygen. And so all the methane would turn into water and carbon perhaps. And this carbon would make things sooty. So this would make a beaker that you were heating, it would cover it in a black substance, which would be the carbon. And also this carbon would glow very brightly in the flame, so your flame would be yellow. Okay, so anyway, that's a little bit of a sidetrack. The key point about incomplete combustion reactions is that they balance, but how you make them balance is kind of up to you, because you can include any amount of carbons and carbon monoxides in the products that you want. Just make sure that you're also forming water. Okay, so alkanes are quite good at burning. Other reactions they're not so good at, and in particular they're not very good at reacting with halogens. Now you might wonder, well, why are we doing this in that case? Well, because alkenes are quite good, and there's a contrast to be made. But anyway, let's stick with alkanes for the moment. Alkanes will react with halogens, but we need bright light to do this. So often you'll see in the equation above the arrow UV, meaning there has to be bright UV light in order to make these reactions happen. They're called substitution reactions. Why are they called that? Because we're swapping one of the hydrogens in the hydrocarbon for a halogen atom. So what you'll see here is that the CH4 loses a hydrogen but gains a bromine atom, and then we're left with HBr. If ethane reacts with chlorine, we're going to swap one of the hydrogens for a chlorine, but we'll be left with HCl. So writing the equations is actually quite simple here. What's a little bit more tricky is the fact that we need to know something called a mechanism for these reactions. So that means we need to know how the reactions happen. In other words, we need to be able to describe the stages that take place. Now, with free radical mechanisms, the first step involves the formation of a free radical. Okay, this is called initiation because it's what gets everything started, and it's why we need the UV light. So, for example, a chlorine molecule could turn into 2 chlorine radicals. We're representing a radical as having a dot. That means it's got an unpaired electron. The UV light causes this split to happen. And if you think about what's holding 2 chlorine atoms together in a chlorine molecule, there's a pair of electrons. Okay? And this type of bond breaking being fission, is called homolytic. It's called homolytic because when we break this bond, so lytic meaning breaking, we end up with two things that are the same. In other words, the electrons in the bond are shared between the two atoms, and we form two of these so-called free radicals. They're called free radicals because they have an unpaired electron, and this makes them extremely reactive because they want to find a partner for this electron. So they'll react with just about anything, including alkanes, which aren't very reactive. So if we imagine that we had some methane and it was reacting with chlorine, that could react with a chlorine radical. Now this would be a different step. Once we'd formed the radicals in the initiation step, we could take part in what is called a propagation step, where one molecule reacts with another. This takes one of the electrons from a carbon-hydrogen bond and makes the HCl that we saw on the previous slide. However, what's left now is CH3 because it's lost a hydrogen atom, but it has now got an unpaired electron. So it's called propagation because although we use up one radical, we've made another. And now this radical that we've just made could potentially react with something else, like perhaps another chlorine molecule, and if it did that, then this electron would pair up with one of the electrons from this bond and we'd make CH3Cl, and we'd produce yet another chlorine radical. So this chlorine radical can now take part in another reaction. Okay, so this is why these are called propagation steps, because although we use up a radical, we make another one. The last step of a reaction, notice here that we have made HCl and CH3Cl, is what is called a termination step. And this is where two radicals collide, because if two things with an unpaired electron come together, like for example these two radicals that we've already seen, then they won't produce another radical. They'll produce something that has all paired electrons, and that's the end, so to speak. Right? You could also end up with two chlorine radicals colliding together, and that would just reform a chlorine molecule. Or you could even end up with two CH3 radicals colliding together, because that would make a totally different product, C2H6, which would be ethane. So it's also important to realize that although we can write quite nice, neat, tidy reaction equations for these, like CH4 plus Cl2 makes CH3Cl and HCl, it's important to realize that there will be lots of other products that form, even though we don't necessarily have to put them into our equation. Okay? And it's definitely important to know the meaning of this term homolytic fission, because we'll contrast that with a different type of fission later on. Okay, so hopefully now that you've watched this film, you know why alkenes are unreactive. You can write equations for combustion reactions and reactions with halogens, and you know what we mean by a free radical mechanism. It's important to practice this stuff, obviously, to get it stuck into your memory. But if you've got any questions or comments, please feel free to come and see me or to post a comment on the YouTube channel.